Ancient builders shaped granite as if it were soft clay. This video will reveal the forgotten machines responsible for this impossible precision, giving you a completely new perspective on human history. We will uncover how stones were cut with laser-like accuracy and why this advanced technology vanished without a trace. By the end, you will see the ancient world not as a primitive past, but as a landscape of lost innovation. What forgotten chapter of human ingenuity are we only just beginning to read? The stones themselves are the first and most stubborn witnesses. At sites like Puma Punku in Bolivia, you are not looking at rough, weathered blocks. You are confronted by a geometric puzzle of andesite and granite, a material harder than steel, cut into forms that defy simple explanation. Each block is interlocked with its neighbors through a series of complex tabs and notches, fitting together so perfectly that you cannot slide a piece of paper between them. This is not just skilled craftsmanship, it is a level of precision that suggests a different manufacturing process entirely. The edges are sharp, the angles are flawless, and the surfaces are often polished to a mirror finish. This same language of impossible stonework is spoken at the base of the Great Pyramid, where massive foundation stones were joined with similar hairline accuracy. The conventional narrative tells us of copper chisels and stone hammers, but these tools simply cannot account for what we see. How do you achieve a perfectly flat surface across a square meter of granite with nothing but a pounding stone? How do you cut intricate, repeating channels into diorite, one of the hardest stones on Earth, with a softer piece of copper? Engineers who examine these cuts, professionals like Christopher Dunn, point out that they exhibit the telltale marks of advanced machining. The consistent grooves and unvarying symmetry suggest the use of a tool that moved with fixed, unerring pressure, something like a massive saw or a milling machine. The precision is so exact that it implies the existence of a standardized measurement system and the machinery to execute it. This was not an artisanal freehand technique. It was production. The stones silently testify to a technology that has since vanished from history, and their perfect, unmortared joints are a permanent question mark etched into the landscape. The stones at Saxehuaman tell a different story from the ground up. Run your hand along the colossal granite blocks, and your fingers might trace a series of perfectly straight, parallel grooves etched deep into the rock. They look less like the erratic scars of hand tools and more like the uniform marks left by a massive, steady saw. This is our first tangible clue. These grooves are often spaced with a rhythmic consistency that the human hand, no matter how skilled, would struggle to replicate over such long distances. The immediate, conventional explanation points to copper saws dragged back and forth with an abrasive like quartz sand. And indeed, experimental archaeologists have shown this method can slowly cut stone. But what they cannot replicate is the unnerving uniformity. The grooves at places like Saxehuaman are not just straight, they are deep and unvarying, as if the cutting tool never wavered, never slowed, and never changed angle. It maintained a constant, immense pressure that a team of people pulling a rope simply could not achieve. This suggests something far more stable and powerful. Imagine a large, rotating blade, perhaps made of a durable material and embedded with even harder abrasives, turning with relentless force. It could be powered by a water wheel or even a large team walking in a circle to drive a central axle. This would not be magic, but simple, clever mechanics. A machine like this would leave behind the exact signature we see, the ghost of its blade preserved in the granite. It transforms the act of cutting from a grueling, unpredictable art into a controlled, repeatable process. This evidence of early machining forces us to ask what kind of mind conceived of such a device. Who understood the principles of rotational force and fixed guides well enough to build them on a scale that could dress a mountain? The grooves are a silent testament to that lost knowledge, leading us directly to the next piece of the puzzle, the tools that have vanished from the archaeological record. But the evidence of cutting is only half the story. Deep within the quarries of ancient Egypt, a second, more startling clue was left behind, not on the surface of the stone, but drilled straight through its heart. Here, researchers like John Anthony West documented the presence of cylindrical holes and the core samples that were sometimes left inside them. These are not crude, pounded-out cavities. When you examine them, you see a perfect circular borehole, and within it, a spiraling groove cut deep into the granite. This groove is the fossilized record of the drill bit's path. It is a continuous, uniform spiral that maintains a consistent depth and pitch from start to finish. This single feature tells us everything. A spiral groove like this is the unmistakable signature of a drill that was rotating at a high, sustained speed while being fed into the rock with immense, constant pressure. It is the same kind of mark a modern drill press would leave behind. Think about trying to create this with a manual, bow-driven drill. A person pulling a bow back and forth would create an erratic stop-start motion. The groove would be uneven, it would waver, and it would show signs of the tool slowing and speeding up. The grooves in the Egyptian granite show none of that. They are flawless. This points directly to a tube drill, a hollow cylinder, likely tipped with an abrasive harder than granite, something like diamond or corundum crystals. This drill bit was not being wobbled by human hands. It was held in a fixed, stable machine. The consistency of the feed rate, the pressure, and the rotation all speak of a power source that was both relentless and precisely controlled. So we must ask, what kind of engine could have provided this force in a world we are told was powered only by muscle and water wheels? The spiral groove is a silent scream of a forgotten technology, and it leads us directly to the question of what fueled these incredible machines. There is a third and perhaps most elegant clue to this lost technology. It sits not in a wall or a quarry, but in a museum case, in the form of a stone vase from Saqqara, Egypt. Carved from a single block of hard stone like diorite or schist, its form is breathtakingly perfect. The curves are fluid and symmetrical, the walls are astonishingly thin, and the surface is a flawless, polished mirror. When you look at it, you are not seeing the idiosyncratic touch of a sculptor's chisel. You are seeing the ghost of rotation. Every contour, every smooth transition speaks of an object that was spun while being shaped. The absence of any erratic hand tool marks is conspicuous. Instead, the symmetry is so absolute that it points to only one plausible explanation: a lathe. Imagine a simple but robust machine, a spindle that rotates the block of stone. A craftsman would then hold a fixed, sharp tool against the spinning stone, perhaps a point tipped with an even harder abrasive. With each pass, the tool peels away a microscopic layer, guided not by a trembling hand, but by the steady mechanics of the machine itself. This could have been powered by a bowstring pulled back and forth, or even a heavy flywheel set in motion by an assistant, storing enough momentum to ensure a smooth, uninterrupted spin. The result is an object of impossible perfection, a vessel that feels less carved and more grown, as if the stone itself flowed into this perfect shape under the command of centrifugal force. The implications of this are staggering. It means the ancient artisans did not just have powerful saws and drills, they understood the fundamental principle of the machine tool, a device that controls the movement of a cutter to produce a predetermined, repeatable form. This knowledge transforms them from mere stoneworkers into proto-engineers, And if they could mount a block of diorite on a lathe to create a delicate vase, what was to stop them from scaling up the principle? The same rotational technology that produced these small, perfect artifacts could have been the very engine behind the massive, precise stonework that still baffles us today. The vase is not just an artwork, it is a blueprint for a forgotten industrial age, pointing toward the monumental machines that must have followed. Yet even the perfect symmetry of a lathe-turned vase does not fully explain the grandest stonework. To find the fourth clue, you must travel to the high Andes and stand before the retaining walls of Ollantaytambo. Here, the stone blocks are not just cut, they are plain. Their surfaces are so impossibly flat that when two are placed together, the gap between them is less than the thickness of a single sheet of paper. This is not merely smooth, it is a geometric perfection that can only be described as machined. You can run your hand over the granite and feel no undulation, no dip or rise, just an unbroken plane stretching for meters. This kind of flatness is a different kind of problem from cutting or drilling. It requires a tool that can move across a vast surface area, removing material with such consistent, microscopic precision that the final product is a plane of near optical quality. Think of a modern milling machine where a cutting head is guided along a fixed track, shaving off thousandths of an inch with each pass. The stones at Ollantaytambo bear the hallmarks of a similar ancient process. A large, guided blade, perhaps a massive bronze plate embedded with diamond-hard abrasives, could have been drawn back and forth across the stone's face. But the key is the guide itself. The tool could not have been held by hand, as the slightest waver would create a visible curve or dip. It had to be mounted on a stable frame, a machine that ensured every single pass was perfectly straight and level, removing material until the surface achieved an almost liquid flatness. Modern experiments with stone abrasives and copper tools can create a smooth finish, but they consistently fail to produce these vast, perfectly planar surfaces. The precision is simply unattainable without a fixed mechanical guide. So how were these planing machines designed? They may have used massive stone rails to guide a cutting sled, or perhaps a swinging arm that moved in a perfect arc, its cutter adjusted after each sweep. The power could have come from teams of workers or even the flow of water, but the intelligence was in the guiding mechanism. This was not brute force, it was applied physics. The existence of such machines suggests a forgotten chapter of engineering, one where the principles of mass production were applied to mountain-sized blocks of stone. What other colossal devices, now lost to time, were once humming in these quarries, shaping the very bones of the earth with impossible accuracy? The stones of Ollantaytambo are not just flat, they are alive with geometry. Step closer to the famous polygonal walls of Cusco or the fortress of Saxehuaman, and the true depth of the mystery reveals itself. You are not looking at simple rectangles. You are witnessing a three-dimensional stone puzzle where each massive block is a unique, irregular polygon with as many as 12 distinct sides. These are not random shapes. They fit together with such seamless, interlocking perfection that the walls have withstood centuries of earthquakes, their complex joints actually absorbing and redistributing the seismic energy. How could such intricate, multi-angled forms be carved and matched with such flawless accuracy? The precision goes far beyond what the human eye and a hammerstone could ever achieve. Each unique block would have required its own precise set of measurements and a corresponding, equally precise cutting plan. This points directly to the use of templates. Imagine a master set of wooden or metal guides, perhaps even full-scale patterns laid out on a flat surface. A stone would be rough cut, then meticulously dressed against these guides, its angles constantly checked until it matched its designated place in the grand design. The cutting tool itself would need to be guided. A simple handheld saw could never maintain the perfect, consistent angles required for these jigsaw-like fits. Instead, picture a pivoting arm, a machine where the stone or the cutting blade could be locked into a specific, preset angle. The stone might be mounted on a turntable, allowing it to be rotated and presented to a fixed blade at the exact orientation needed for each cut. The abrasive, perhaps a slurry of water and crushed quartz sand, would then do the work, but the machine would control the path. This was not guesswork, it was applied mathematics. The builders possessed a profound understanding of geometry, capable of calculating compound angles and visualizing how these massive, irregular forms would lock together into an indestructible whole. This sophistication suggests that the stone cutting machines were part of a larger, integrated system. The same culture that engineered the lathe, the drill press, and the planing machine also possessed the mathematical genius to design these earthquake-proof walls. The stones themselves are the final proof, a frozen symphony of angles and forces that could only have been composed with the aid of forgotten technology. What kind of society possessed such a complete and unified knowledge, and why did the machines that built these wonders vanish so completely from history? This mirror-like finish on the pyramid's casing stones is our sixth, and perhaps most revealing, clue. You can still see traces of it on the few remaining blocks at the base of the Great Pyramid, a surface so incredibly smooth and reflective that it feels like glass under your fingertips. Achieving this on granite, a stone composed of hard, crystalline minerals, is an entirely different challenge from simply shaping it. Rubbing it by hand with sand and water would take a lifetime and still never produce such a uniform, optical-grade polish. The consistency of the finish, spread over thousands of square meters, points directly to a mechanized process. Imagine a large, rotating head, perhaps a disc of felt or leather, charged with a fine paste of increasingly refined abrasives. This machine would have moved across the stone surface with unwavering pressure and speed, systematically grinding down microscopic imperfections until all that remained was a perfect, reflective plane. The ancient artisans would have started with a coarse grit, maybe crushed quartz, and progressively moved to powders as fine as emery or even diamond dust, each pass removing the scratches left by the previous larger grains. This step-by-step refinement is the core principle of modern industrial polishing, and the evidence suggests the pyramid builders understood it perfectly. The efficiency of such a system is staggering. A single machine, perhaps powered by a team of workers turning a capstan or even by a flowing water channel, could polish vast areas in a fraction of the time it would take an army of laborers working by hand. This was not just about beauty, it was about achieving a finish with functional precision. A perfectly flat, polished surface creates a stronger, more stable bond when joined with another, and it better resists weathering over millennia. But this brilliant solution forces a practical question. What were these advanced abrasives, and where did they come from? The pursuit of this flawless finish leads us down into the earth itself, to the mines and quarries that supplied the raw power for these forgotten machines. The final clue is etched in plain sight, not in the stone's shape, but in the words and images carved upon it. Look closely at the vast fields of hieroglyphs covering Egyptian temple walls. The characters are not just beautifully rendered, they are unnervingly uniform. Each repeated symbol, every complex glyph, is a perfect copy of the last, with lines of identical depth, width, and spacing. This is a level of consistency that the human hand, no matter how steady, simply cannot maintain over thousands of characters. There are no slips, no corrections, no variations in the depth of the cut that would betray a craftsman's tired arm or a momentary lapse in concentration. This perfection points toward a form of mechanical reproduction. Imagine a device much like a pantograph, a system of linked arms and levers that allows an operator to trace a pattern on a small master template. As the user guides the tracer, the machine's cutting arm, holding a sharp, vibrating bit, would precisely duplicate the movement onto the stone surface, scaling it up to the required size. This would not be a futuristic technology, but a brilliantly simple mechanical aid. An artisan could create one perfect prototype of a hieroglyphic panel, and then the machine could replicate it endlessly across a wall with flawless accuracy, saving immense time and effort while guaranteeing a uniform result. The evidence for this is in the stone itself, in the absolute lack of human error and the machine-like precision of every line. This raises a profound question. If such devices were used for the delicate work of inscription, how widespread was this knowledge? Could the same principle of guided replication have been used in other ancient cultures? From the perfectly repeated motifs on Mesopotamian cylinder seals to the standardized runes on Nordic standing stones, the ghost of the machine may be hiding in the art we thought was made entirely by hand. This forgotten technology of replication suggests a prehistoric world more connected and more mechanically ingenious than we ever supposed. These precise stone cuts are a global phenomenon, appearing in cultures separated by vast oceans and thousands of years. In the highlands of Peru, the polygonal walls of Saxehuaman lock together in a giant's jigsaw puzzle. Then, across the Pacific in Japan, you find the very same language written in stone at the base of the Saxehuaman burial mounds, where massive, irregular blocks are fitted with that same hairline precision. How could two cultures with no known contact arrive at an identical and incredibly complex solution for building earthquake-resistant walls? The similarities do not stop at fitting techniques. The same evidence of advanced drilling appears in both pre-Incan and ancient Egyptian sites, with those telltale spiral grooves bored deep into granite. The same obsession with mirror-smooth polishing is found on the granite slabs of Osirian in Egypt and the andesite blocks of Tiwanaku in Bolivia. This is not a coincidence. It suggests one of two profound possibilities. Either this knowledge of advanced stone-working machinery was developed independently in separate corners of the globe, a case of parallel inventions solving the same engineering problems. Or there was a flow of information, a network of exchange that we have yet to uncover. Picture a trade route not for spices or silk, but for ideas, where the designs for a revolutionary tube drill or a planing machine were the most valuable cargo of all. This shared technological signature forces us to reconsider the entire map of the ancient world. Were these cultures more connected than our history books admit? Or does it point to a common, older source of knowledge that they all drew upon, a lost foundational civilization whose machines became the blueprint for the world's greatest monuments? This global pattern is the final, undeniable proof that we are not looking at isolated acts of genius, but at the scattered pages of a single, forgotten instruction manual. And this raises the most practical question of all. What force was powerful enough to drive these machines across continents? The sheer scale of these operations forces a practical question. How were these machines actually powered? One of the most enduring theories points to the raw, organized strength of human and animal labor. We know from historical records that massive workforces were mobilized for these projects. It is not difficult to envision a team of workers walking in a circle, pushing long levers to rotate a massive capstan. This central drum, wound with ropes, could have transferred that rotational force to operate a large cutting saw or even power the spindle of a drilling apparatus. A system of wooden gears and pulleys could have amplified this human effort, creating the immense, sustained pressure needed to plane a granite block. This method is mechanically sound and fits within the known technological framework of the ancient world. A treadmill, powered by men or even oxen, could provide a similarly steady input for a polishing machine, its large rotating head moving relentlessly across a stone surface. The rhythmic, collective labor of hundreds could indeed have been the engine behind the stonework. Yet, when we look at the evidence left in the stone itself, this theory begins to strain. The perfectly uniform spiral groove inside a granite drill core tells a story of more than just steady power. It speaks of high, unvarying rotational speed. A team of men walking a capstone produces a powerful but relatively slow rotation. To achieve the cutting speed implied by that fossilized groove, the machine would have needed a way to multiply that rotation dramatically, perhaps through an intricate series of gears we have no evidence for. The consistency is the true challenge. Human labor is inherently variable. Workers tire, their pace slows, the rhythm breaks, but the marks on the stone show no such variation. The feed rate and the rotation are locked in a perfect mechanical harmony from start to finish, as if driven by a force that never wavered. So while human and animal power could explain the brute force, it struggles to account for the flawless precision and the implied speeds. This gap in the theory pushes us to look beyond muscle and rope toward a power source that was both relentless and precisely controllable, something that could have turned these machines into the ancient equivalents of modern industrial tools. What other forgotten energy, harvested from the world itself, could have provided the missing heartbeat for these forgotten engines? But muscle and rope alone cannot explain the relentless consistency etched into the granite. There is another, more elegant power source that fits the evidence perfectly: the timeless flow of water. Ancient civilizations were master hydrologists, and the Romans famously harnessed rivers with sophisticated water mills to grind grain. The leap from grinding flour to cutting stone is not a large one. Imagine a fast-moving channel diverted from a river, directing its full force onto a large water wheel. The wheel's axle could be connected to a crankshaft, transforming the water's linear push into a powerful, rotating motion. This rotation could then drive a long, reciprocating saw blade, its teeth embedded with crushed diamonds or emery, gliding back and forth against a block of granite with a rhythm that never tired, never slowed. Or through a system of gears, that same water power could spin a drill head at a dizzying, constant speed, forcing a tubular bit deep into the heart of the stone. The unvarying pressure and rotation needed to create those perfect spiral grooves in the Egyptian drill cores finds its perfect engine in the hydraulic hammer of a flowing river. This was not brute force, it was harnessed nature, and the geography itself supports this theory. Many of the most mysterious ancient sites, from the quarries of Aswan to the highland complexes of Peru, are situated near powerful, reliable water sources. The builders did not just settle near water for drinking, they built their industrial power grid around it. The logistics of such a system are fascinating to consider. How would they have constructed and maintained these hydraulic networks? They would have needed sluice gates to control the flow, settling ponds to filter abrasive silt, and durable, waterproof bearings for their axles, perhaps made from hardened wood or even bronze. This was large-scale, organized engineering. The presence of such machinery transforms our image of these sites from silent, sacred spaces into bustling, water-powered workshops, humming with the sound of flowing water and grinding stone. This elegant solution, however, leads to a final, tangible mystery. If these machines were real, what were they actually made of? The search for their power source brings us face to face with the materials that have vanished from the record. The relentless hum of these machines would have been useless without a bite far harder than bronze. To cut granite, you need a substance that can defeat granite. This is where the theory of advanced abrasives enters the story. turning these hypothetical devices from simple mechanisms into truly formidable tools. The ancient world was not devoid of such materials. Diamonds, corundum, and emery, all harder than quartz, were known and traded along extensive networks that stretched from the mines of India to the workshops of Egypt and the Mediterranean. An artisan might have called them by different names, but they understood their power. The key was not just having these super-hard grains, but how they were deployed. Picture a massive bronze saw blade, its edge not sharpened to a fine edge, but instead embedded with a continuous line of crushed diamond particles, held in place by a resin or a softer metal. This is not a futuristic concept, it is the direct ancestor of the diamond-tipped blades we use today. Drawn back and forth by a water-powered machine, such a blade would slice through granite not by shearing it, but by grinding it away, a slow, inexorable process that left behind the unnervingly straight and parallel grooves we find. The same principle applies to the drill cores, a hollow copper tube, its end charged with a paste of diamond dust and oil, rotating at high speed, would effortlessly bore into the hardest stone, leaving its signature spiral groove as a permanent record of its passage. The efficiency of this system cannot be overstated. A single diamond-embedded blade could dress hundreds of blocks before wearing out, making the construction of massive projects logistically feasible. But where is the physical evidence for such tools? The machines themselves, likely made of valuable and reusable metals, were almost certainly melted down and repurposed over the millennia. The abrasives, however, are a different story. Archaeologists have unearthed grinding stones and polishing pads from ancient Egyptian sites that still bear traces of corundum powder, a material harder than quartz. They have found raw emery, a natural mix of corundum and magnetite, in Minoan workshops on Crete, while a lone diamond chip has never been found nestled in a Bronze Age toolbox. The trading routes that could have delivered them absolutely existed. The presence of these super-hard abrasives in the archaeological record, often in contexts associated with lapidary work and stone vessel production, provides a tangible link. It confirms that the ancient artisans possessed the raw mineral power to make their machines cut with impossible precision. They had the engine, they had the blueprint, and crucially, they had the teeth. This brings us to the final, haunting question, a mystery that has lingered over every perfectly cut stone. If they had all the components for a proto-industrial revolution, what happened to it? Deep in the river deltas of Costa Rica, a different kind of artifact sits silently in the jungle, one that challenges our understanding of ancient craft. These are the stone spheres, some as small as a baseball, others larger than a car and weighing many tons. They are not merely round rocks. Their perfection is unnerving, a geometric purity so exact that modern surveyors have found their diameters to be nearly identical, with deviations measured in mere millimeters. This is not the work of pecking and grinding with hand tools. The surfaces are smooth, often polished to a high sheen, and the curvature is flawlessly consistent from every angle. You are not looking at a sculptor's interpretation of a sphere, you are looking at the product of a machine. The most plausible explanation points directly to a process of rotational shaping. A massive block of granodiorite, a hard, igneous rock, would have been mounted between two pivots and set spinning. As it rotated, artisans could have applied a fixed cutting tool, or more likely, a constant stream of abrasive slurry, a wet paste of sand and water, or perhaps something harder like crushed quartzite. With each revolution, the high points of the stone would be ground down, the machine tirelessly correcting its own form until only a perfect sphere remained. To achieve such uniformity across hundreds of these objects, the process must have been guided. It is easy to envision a simple wooden template, a circular cutout of the desired diameter, that was constantly held against the spinning stone to check its progress. This combination of rotational force, abrasive technology, and quality control is the hallmark of an advanced, systematic production line. But crafting these perfect forms was only the first step. The largest spheres were quarried from sites miles away from where they were ultimately placed, often on high bluffs or deep within river basins. Moving a 16-ton sphere of flawless granite through dense jungle and across rugged terrain without chipping or scratching it is a logistical nightmare. It speaks of a society with sophisticated knowledge of leverage, rollers, and perhaps even barges for river transport. The sheer effort implies that these spheres held a profound, perhaps sacred significance, their perfect geometry representing something essential to the culture that made them. Yet their ultimate purpose remains one of archaeology's most stubborn mysteries. Were they astronomical markers, symbols of power, or components in a vast, unseen celestial calendar? The stones give no answer. They simply sit, these perfect orbs, as a silent testament to a people who had mastered the art of the machine, only to have the reason for their labor vanish into the jungle behind them. The largest cut stones on Earth lie half buried in a Lebanese quarry. At Baalbek, 3 colossal blocks known as the Trilithon wait silently, each one a staggering 1,000 tons of precision-dressed limestone. Their scale is not merely impressive, it is physically disorienting. To move a single one of these behemoths today would require the combined force of multiple modern cranes, yet they were shaped and positioned with an accuracy that defies simple leverage. The edges are sharp and true, the surfaces are flat, and the joints between them are almost invisible. This is not the work of ramps and ropes alone. The precision of the cuts implies the use of massive, guided saws, blades so large they would need a fixed frame to operate. Imagine a timber gantry towering over the stone, from which a gigantic bronze-edged saw, charged with an abrasive slurry, is suspended. Teams of workers would pull it back and forth, its path controlled by the rigid frame, ensuring every cut was perfectly straight and plumb. The lifting of these stones presents an even greater puzzle. How do you raise a 1,000-ton block and lower it into place with hairline accuracy? The answer may lie in a system of counterweights and levers on a scale we seldom consider. Enormous wooden cranes, powered by human labor walking within giant treadwheels, could provide the lifting force, while a clever arrangement of counterbalanced weights would allow for minute-controlled adjustments. Placing the stone would be a ballet of brute force and delicate precision, our operation requiring not just muscle, but a deep understanding of physics and geometry. This level of coordinated effort points to something far beyond a simple society of stonemasons. It reveals a highly organized civilization, one with master engineers, a structured labor force, and the logistical genius to manage a project that would be daunting even with modern technology. The stones of Baalbek are more than a monument. They are the blueprint of the society that built them, a society whose name is lost to time, but whose engineering prowess is carved into the very bedrock. The very machines that could shape mountains may have been undone by the silence that surrounded them. The principles of these devices were not carved on public monuments for all to see. Instead, this powerful knowledge was likely guarded with intense secrecy, held within closed guilds or schools of master craftsmen. In an age before patents, a revolutionary stone-cutting technique was not just an intellectual achievement, it was a source of immense political power and economic advantage. The designs for a water-powered saw or a diamond-tipped drill would have been state secrets, passed down through generations of a chosen few in an oral tradition. A master would teach his most trusted apprentice not with blueprints, but through demonstration and memory, revealing the machine's intricacies only after years of testing and loyalty. This system of knowledge transfer was both its strength and its ultimate fragility. It protected the technology from rivals, but it also made the entire enterprise vulnerable. A single generation of disruption, a war that scattered the initiates, a famine that decimated the guild, or a cultural shift that devalued the old ways, and the chain of transmission would be broken forever. The technical details, the precise angles of a gear, the exact mixture for an abrasive slurry, all of it could vanish in a handful of decades, leaving behind only the impossibly perfect stones as a monument to a process no one could remember. This secrecy adds a profound layer to the mystery. We are left to piece together the blueprint from the finished product, like trying to reverse engineer a car from a photograph. Modern engineers and archaeologists are now attempting to do just that, building their own versions of these hypothetical machines. They use period-appropriate materials, bronze tools, wooden frames, and abrasives like quartz sand, putting these replicas to the test on real stone. Some experiments have shown promise, creating clean cuts and smooth surfaces, yet the results often lack the flawless, industrial precision of the ancient originals. The gap between their best efforts and the ancient work hints at lost nuances, the secret tricks and calibrations that died with the last master craftsman. So how do we recover what was so deliberately concealed? We must become apprentices to the stones themselves, learning to read the subtle language of the tool marks they left behind. Modern experiments in stone cutting are a humbling exercise. Archaeologists and engineers have built replicas of what they believe ancient tools to be, using copper saws and drills with quartz sand as an abrasive. The results are telling. While these tools can indeed cut stone, the process is agonizingly slow, and the results are far from perfect. A copper saw, dragged back and forth by a team of people, creates a cut that is often wavy and uneven. The sand abrasive becomes embedded in the soft copper, losing its cutting efficiency quickly and requiring constant reapplication. The finished surface is rough, bearing little resemblance to the laser-straight grooves and mirror finishes found on ancient granite. These experiments prove that the basic method is possible, but they completely fail to achieve the scale, speed, and precision that the archaeological evidence demands. The gap between what we can replicate with simple hand tools and what the ancients actually accomplished is a chasm. This discrepancy is the strongest argument for the machine theory. It suggests that the copper and the sand were merely components in a much more sophisticated system. The copper was not the cutting tool itself, but perhaps the holder for a harder, industrial-grade abrasive. The sand was not thrown on haphazardly, but was likely part of a controlled slurry, pumped or fed directly onto a blade spinning at high speed. These modern attempts are not failures, they are vital clues. They show us the ceiling of simple manual labor, a ceiling that the ancient builders clearly shattered. So what does this mean for our understanding of the past? It forces us to stop looking for simpler answers and to start accepting the evidence staring back at us from the stone. The perfection was not an accident, and it was not achieved through sheer force of will. It was engineered. Another theory challenges the very nature of the stone itself. What if these perfectly fitted blocks were not quarried and cut at all, but were instead poured into place like a modern concrete? This is the radical proposal of the geopolymer theory, championed by researchers like Joseph Davidovits. He suggests that the ancient Egyptians, and perhaps other cultures, had developed an advanced form of chemistry, creating a synthetic stone from a slurry of crushed limestone, clay, and special alkaline activators. This liquid rock could have been carried in baskets to the construction site, then poured into wooden molds, fusing into a solid, seamless block that perfectly matched its neighbors. This would elegantly explain the absence of tool marks on some surfaces and the incredible puzzle-like fits of certain walls. The need for massive saws and drills would vanish, replaced by the quiet chemistry of a slurry basin. Yet, for all its appeal, this theory walks into a storm of contradictory evidence. The very quarries that supposedly provided the raw crushed materials still exist, showing clear evidence of blocks being extracted, not just mined for aggregate. At Aswan, the famous unfinished obelisk remains attached to the living bedrock, a monument to the traditional quarrying process. More critically, the tool marks we have followed so meticulously cannot be so easily dismissed. The telltale parallel grooves from saws, the spiral drill cores deep within solid granite, and the lathe-turned vases all speak of a subtractive process where material was removed from a solid block, not added in a mold. Geopolymer might explain some of the softer limestone blocks, but it struggles to account for the work on granite and diorite, stones that require immense heat to melt and reconstitute, a process far beyond even some modern capabilities. So where does this leave us? Perhaps the truth is not a single answer, but a spectrum of technologies. Maybe the builders used both methods, casting softer stones for certain applications while deploying their powerful machines to conquer the hardest granites. This hybrid approach paints a picture of a truly sophisticated industrial culture, one that commanded a diverse toolkit of both chemistry and mechanics. The real mystery then deepens because mastering both casting and machining requires an even broader base of knowledge. How did such a comprehensive system of innovation arise, and why did it leave behind no written formulas or engineering plans for us to find? The quarries themselves hold the final, undeniable proof. Walk through the granite quarries of Aswan, Egypt, and you are standing in an ancient factory floor frozen in time. Here, the famous unfinished obelisk still lies in its bedrock cradle, and its surfaces are not blank. They are covered in deep, parallel channels, the unmistakable tracks of massive saws that were meant to separate this 1,000-ton monument from the earth. These are not the chaotic scars of countless hammer strikes. They are straight, purposeful, and spaced with a rhythmic consistency that reveals a systematic process. You can still see where the workers marked their cutting lines and then followed them with a tool that never wavered. This was not a freehand operation. It was a guided one. Imagine teams of workers not just pulling a rope, but operating a large, weighted saw frame that ran along a set track or a taut guide wire. This frame would hold a bronze blade, perhaps many meters long, and as it was drawn back and forth, a slurry of water and abrasive sand would be poured into the cut. The water did more than just keep the dust down. It cooled the metal and carried the abrasive deep into the incision, allowing the gritty particles to constantly grind fresh stone. The scale of these cuts is staggering. The channels around the obelisk are deep enough for a person to stand in, a testament to the relentless, mechanical repetition of the saw's motion. This direct evidence transforms the quarry from a simple source of stone into a sophisticated workshop. What does this tell us about the scale of their ambition? The presence of such organized, large-scale cutting implies a production line mentality. They were not just extracting blocks, they were prefabricating monumental architecture with a level of planning and precision that rivals modern engineering. This was an industry. It required foremen, engineers, logicians, and a vast support system to feed, house, and direct the workforce. The economic and social impact must have been profound, centralizing power and resources in a way that reshaped entire civilizations. The quarry marks are the faded blueprints of that lost industry, a silent echo of the day the machines fell silent and the obelisk was left forever waiting in the sun. The silent quarries of Aswan reveal more than just tool marks. they expose the economic engine of an empire. The deployment of advanced stone-cutting machines would have fundamentally reshaped ancient labor and accelerated construction on an unimaginable scale. Consider the sheer manpower required to shape a single 1,000-ton block with primitive tools. It would take a small army of workers years to pound, grind, and polish it into submission. But a team of skilled operators guiding a water-powered saw could achieve the same result in a fraction of the time with a fraction of the people. This was not just about saving effort, it was about compressing time itself. A pharaoh's ambitious pyramid complex, which might have taken a lifetime to complete with hand tools, could instead be finished within a single reign. The labor force, often imagined as endless ranks of slaves, transforms under this new light. Instead of millions of unskilled workers straining against ropes, we see a smaller, highly specialized class of engineers and machine tenders. These were the ancient equivalent of technicians, individuals who understood hydraulics, abrasives, and the precise calibration of a cutting frame. Their expertise would have been incredibly valuable, freeing up a massive portion of the population for agriculture, warfare, or the arts. This technological efficiency becomes a powerful political tool. A ruler who commanded these machines could launch monumental projects that cemented their divine status and political control, projects that would have been logistically impossible for a rival relying on manual labor alone. The sudden ability to build faster and grander than anyone else could have been the decisive factor in the rapid rise of an empire. Yet this very dependence on advanced technology creates a profound vulnerability. What happens when that knowledge is lost? The society that once flourished by building with machines would eventually find itself unable to maintain them, let alone reproduce them. The fall of such a civilization would not be a slow decline, but a precipitous drop. The great-great-grandson of a master machinist might stare at a broken water wheel gear, possessing neither the blueprint nor the understanding to fix it. The stones for a new temple would remain rough-hewn in the quarry, and the cultural momentum that drove the empire would stall. The technology that enabled their golden age would become the very anchor that dragged them into a dark age. How different would our history books look if we factored in these cycles of technological boom and bust? The perfection in the stone is not just a mystery of engineering, it is a ghostly imprint of an ancient economy, one that was capable of industrial-scale achievement before vanishing without a trace, leaving behind only the silent, perfect stones as a measure of what was lost. History is littered with the ghosts of forgotten technologies. The formula for Greek fire, a terrifying incendiary weapon that burned even on water, vanished with the Byzantine Empire. The precise recipe for Roman concrete, a material that endures in harbors for millennia while our own modern concrete crumbles, was lost for centuries. These are not isolated incidents. They reveal a recurring pattern of human history, a cycle of profound discovery followed by catastrophic loss. The machines that shaped stone with impossible precision almost certainly fell victim to this same cycle. Their disappearance was likely not a single event but a slow fade, a death by 1,000 cuts. A prolonged drought could have dried up the water channels that powered the saws. A devastating invasion might have slaughtered the guild of master engineers, the sole keepers of the machine's blueprints. Or perhaps a new religious or political order simply devalued the old ways, seeing the colossal construction as a symbol of a past they wished to erase. The knowledge so carefully guarded and orally transmitted would have had a very narrow path to survival. Once that path was broken, there was no backup, no library of schematics to consult. The machines themselves, made of valuable bronze and timber, would have been scavenged, melted down for weapons, or left to rot. Within a generation or two, the very memory of how to build them would have faded into myth, leaving behind only the stones as impossible, silent monuments. This cycle forces a sobering reflection on our own technological age. We live in an era of digital abundance where we believe our knowledge is permanently preserved on servers and in the cloud. But how fragile is this foundation really? Our entire digital world depends on a fragile chain of electricity, rare earth minerals, and global supply chains. A single, large-scale solar flare or a protracted global conflict could sever that chain, rendering our vast digital libraries as unreadable as a shattered tablet. The stones of Puma, Punku, and the pyramids are a permanent lesson in the fragility of human innovation. They ask us a direct and urgent question. What are we doing today to ensure that the core knowledge of our civilization, from agriculture to medicine to energy production, is preserved in a form that is truly resilient, that can survive the collapse of the very systems that created it? The silent stones are a warning carved not in words but in granite, reminding us that no technology, no matter how advanced, is immune to the slow erosion of time. The silent stones of Puma Punku are a permanent lesson in the cost of forgetting. They demonstrate with brutal clarity that a technology, no matter how advanced, is only as durable as the system created to preserve its knowledge. The ancient master builders, for all their genius, operated within a closed system of guilds and oral tradition. Their greatest strength, secrecy, became their ultimate vulnerability. A single broken chain of apprenticeship, one generation lost to war or famine, and the intricate understanding of gear ratios, abrasive slurries, and hydraulic power vanished forever. The machines fell silent not because they were impossible, but because the instructions for building them were never widely shared. This historical fragility forces a direct and urgent question for our own civilization. We live in an age of unprecedented information, yet our own knowledge faces unique and modern threats. Digital archives can be corrupted, file formats can become obsolete, and the very hardware we use to read them can turn into plastic and silicon fossils in a matter of decades. Our modern equivalent of the oral tradition is a server farm, vulnerable to cyber attacks, solar flares, or simple societal collapse. The lesson from the stones is that we must be more deliberate. We must champion open-source knowledge, where the blueprints for our most critical advancements, from medicine to energy production, are stored in multiple, redundant, and analog forms. Imagine if the ancient engineers had inscribed the principles of their lathes and saws on clay tablets and buried them in 1,000 different locations. Their technology might have been rediscovered and rebuilt centuries later. We have the same opportunity today. By committing to rigorous, multi-format documentation and by freely sharing knowledge across disciplines and borders, we build a foundation that is truly resilient. This principle of open documentation transcends archaeology. In medicine, sharing research data accelerates cures. In engineering, publishing failure analyses prevents others from repeating costly mistakes. In agriculture, preserving heirloom seeds safeguards our food supply against disease and climate change. The interdisciplinary insight is that knowledge hoarded is knowledge eventually lost, while knowledge shared becomes a permanent part of the human toolkit. The silent stones ask us to look at our own world and consider what we are doing to ensure that our greatest discoveries do not suffer their same fate, becoming beautiful, baffling monuments to a brilliance that was allowed to fade away. The silent stones cannot speak, but we have learned to listen with new ears. The most profound breakthroughs in understanding these ancient machines are no longer coming from a single field of study, but from the vibrant crossroads where archaeology, engineering, and materials science converge. This is not a solitary pursuit, it is a collaborative symphony. Picture an engineer examining a three-dimensional scan of a drill core from Egypt, her software tracing the unvarying pitch of the spiral groove to calculate the precise feed rate and rotational speed of the tool that made it. Meanwhile, a materials scientist analyzes microscopic residue embedded in a saw cut from Peru, identifying traces of corundum abrasive that confirm the use of a cutting compound harder than quartz. The archaeologist provides the context, placing these technical findings within the timeline of a specific dynasty or culture. Separately, these experts see only fragments. Together, they begin to assemble the blueprint of a forgotten machine. This interdisciplinary approach transforms speculation into testable theory. Research teams now use laser scanners to create perfect digital models of entire walls, revealing patterns in the stonework that are invisible to the naked eye. These models allow them to virtually test how stresses flow through a polygonal wall during an earthquake, proving the engineering genius behind its design. They can simulate the path of a saw blade, adjusting its speed and pressure in a digital environment to see what combination produces the exact mark found on an ancient block. This collaborative spirit then moves from the digital world into the physical. Workshops are held where a master stonemason, guided by an engineer's calculations, attempts to build a full-scale replica of a water-powered saw using only period-appropriate materials. They experiment with different wooden frame designs, various abrasive slurries, and team-based power sources, learning through hands-on failure and success what the ancient builders would have discovered through trial and error. Each broken blade or inefficient gear teaches a lesson, inching the team closer to a functional reconstruction. This process does more than just solve an ancient mystery. It fosters a powerful cycle of modern innovation. The challenges posed by these hard stones push engineers to develop new scanning technologies and more durable cutting materials, advancements that then ripple out into modern manufacturing and construction. We are not just learning about the past, we are building a better future by engaging with its most stubborn puzzles. The question now is, what new tools are emerging to help us see even deeper into the stone, to read the final, faintest lines of this ancient instruction manual? These silent stones now speak through the hum of modern scanners. Advanced imaging technologies like LiDAR and CT scanning are allowing us to peer inside the granite without ever touching its surface. We can now map microscopic tool marks and internal fractures with a clarity that was unimaginable just a generation ago. Picture a research team directing a laser scanner across a single block from the Great Pyramid's core. The device fires millions of light pulses, building a three-dimensional point cloud of the surface with sub-millimeter accuracy. This digital ghost reveals patterns invisible to the human eye, a series of perfectly parallel striations running across the stone. These are not the random scratches of dragging a block, but the consistent, rhythmic signature of a fixed blade moving back and forth with mechanical precision. In another lab, a CT scanner, similar to those used in hospitals, can peer into the heart of a stone artifact. It can detect density variations that betray hidden structures, like the subtle, spiraling fracture pattern left by a high-speed drill deep inside a granite core. This non-invasive analysis is revolutionary because it preserves these priceless artifacts completely intact while giving us entirely new data. It transforms a static monument into a dynamic archive of its own creation. How has this changed our perspective? It forces a quiet revolution in archaeology. We are no longer limited to what we can see under the sun or what we risk by taking a physical sample. We can now collect terabytes of empirical evidence from a single stone, evidence that consistently points toward advanced machining. This data opens the door to re-evaluating every historical narrative we thought was settled. If one block tells a story of saws and drills, what might an entire scanned wall reveal about the forgotten factory that built it? The very existence of these machines forces us to redraw the map of human progress. Our conventional timeline, a steady upward slope from primitive to advanced, begins to crumble under the weight of this evidence. We are taught that the Industrial Revolution was a unique event, a sudden explosion of mechanical ingenuity that began in the 18th century. But what if it was not the first, but merely the most recent? The precision stonework scattered across the globe suggests an earlier, and perhaps entirely separate, peak of innovation. This was not a pre-industrial society dabbling with simple tools. It was a culture that had already mastered the core principles of the machine tool, controlling a cutter's path to achieve a predetermined, repeatable form. This knowledge transforms the ancient world from a place of myth and manual labor into a landscape humming with proto-industrial activity. The implications are staggering. If the pyramid builders used powered saws and drills, then the zenith of their technological prowess must be pushed back, not by centuries but by millennia. Their golden age was not the beginning of their story, but the magnificent culmination of a long, lost period of development, a forgotten era of invention where the blueprint for the lathe and the drill press was first conceived. This revised history asks a difficult question. How many times has humanity climbed this technological mountain only to fall and have to rediscover the path? Our current civilization, with its digital networks and global industry, feels unprecedented, but the stones whisper that we may be walking a path others have walked before. This perspective does not diminish our achievements, but it does instill a profound sense of humility. It encourages us to look at every ancient myth of a lost age or a great flood not as mere fantasy, but as a possible, fragmented memory of a real collapse. What other chapters of human ingenuity have been entirely erased from our history books? The machines that shaped stone are just one clue. This new approach, this willingness to question accepted theories, could unlock other mysteries. It might explain the precise astronomical alignments of monuments we consider primitive, or the sophisticated medical knowledge found in the oldest texts. The next great discovery may not be a new tomb or a golden artifact, but a re-examination of a tool mark we have seen 1,000 times, finally understood for what it truly is, the signature of a forgotten engineer. The possibility of a single, intact discovery electrifies every researcher in this field. What if a sealed tomb, untouched for millennia, holds not golden treasures but the machine itself? A wooden frame, its bronze fittings still holding the ghost of a blade, preserved in the dry desert air. Or perhaps a stonecutter's hoard, buried for safekeeping, containing a full set of drills, saw blades, and the hardened abrasive cores that gave them their bite. Such a find would be more valuable than any jewel, providing a complete blueprint for reconstruction. It would transform our speculation into a working model, confirming the precise mechanics of feed rates, gear ratios, and power transmission. This dream is not pure fantasy. Ongoing excavations at sites like Göbekli Tepe continuously push back the dates of monumental construction, revealing new layers of sophistication with every season. Each new trench dug, each new sensor scan of the ground, carries the potential to uncover a lost workshop, a place where these tools were maintained and stored. The very soil beneath our feet might conceal the answers we have been scraping from the surfaces of finished stones. This tangible hope is what drives continued research, fueling both academic digs and the passionate work of independent investigators. For enthusiasts watching this, the search is not a closed book. You can contribute by following the work of archaeologists in the field, supporting their publications and crowd-funded projects. More directly, you can learn to read the stone yourself. When you visit an ancient site, look beyond the grand scale and examine the fine details. Photograph tool marks, note the patterns of wear, and share your observations with online communities dedicated to alternative archaeology. Your fresh perspective, untrained by conventional expectations, might spot a crucial detail that experts have overlooked: the collective effort of thousands of eyes, both professional and public, poring over this global puzzle, is our greatest tool for finally hearing the story these silent stones have been trying to tell us all along. The quiet hum of discovery is no longer confined to university labs and funded excavations. Some of the most compelling insights into these lost machines are now emerging from garages, backyards, and online forums, powered by a global community of amateur researchers and independent scholars. These modern-day tinkerers are driven by a shared obsession, building physical replicas of proposed ancient saws and drills to test their feasibility with their own hands. A woodworker in Germany might construct a scale model of a water-powered reciprocating saw, meticulously documenting the blade's wear and the type of cut it leaves on a granite sample. Meanwhile, a retired engineer in Ohio analyzes the feed rate on a homemade lathe, experimenting with different abrasive slurries to see which one produces the closest match to the spiral groove found in an Egyptian drill core. Their collective findings, shared instantly across digital platforms, create a living, breathing database of practical experimentation that traditional archaeology often lacks the time or resources to pursue. This grassroots effort brings a powerful diversity of perspective. A master machinist might spot a detail in a tool mark that an archaeologist would overlook, recognizing the subtle signature of a specific type of guide, bearing, or gear train. An artist might intuitively understand how the flow of a polishing compound would interact with a spinning stone surface. This collaborative, open-source approach allows for rapid iteration and failure, a process of elimination that is essential for reverse engineering any complex technology. Yet this vibrant ecosystem of discovery is not without its ethical challenges. The same global network that shares data can also spread unverified claims and sensationalized theories at lightning speed. The line between responsible experimentation and reckless damage to authentic sites is a fine one. How do we encourage this vital, hands-on curiosity while also instilling a deep respect for the preservation of irreplaceable ancient monuments? The answer lies in fostering a culture of responsible exploration, one where citizen scientists are encouraged to channel their passion into non-destructive analysis, digital modeling, and collaboration with academic institutions. When a hobbyist's garage experiment is guided by archaeological data, and when a professor's theory is tested by a skilled craftsman, the divide between amateur and professional dissolves. Together, they form a 21st century guild, piecing together the broken chain of knowledge one careful experiment at a time. Our pursuit of these lost machines carries a profound responsibility. Every ancient site is a non-renewable library, its stones holding chapters of a story we are only beginning to read. The same grooves and drill cores that reveal advanced technology are also incredibly fragile, vulnerable to the careless scratch of a tourist's backpack, the misguided tap of a hammer, or the destructive greed of a looter seeking a souvenir. Each act of damage erases data permanently, like tearing a page from that library before we have even learned its language. This forces us to balance an intense thirst for knowledge with a solemn duty to preserve. We must apply the same ingenuity we admire in the ancients to the science of modern conservation. This means using non-invasive ground-penetrating radar to map subterranean workshops instead of digging them up recklessly. It means employing three-dimensional laser scans to create perfect digital twins of entire sites, allowing global research without a single physical touch. For visitors, it translates to responsible tourism, following marked paths and understanding that these are not just picturesque ruins, but the sacred heritage of living cultures and the fragile legacy of all humanity. Regulated, scientific excavations become a form of meticulous archaeology, where every grain of soil is sifted for information and every finding is meticulously documented before a stone is ever moved. This ethical approach ensures that the mysteries are solved without destroying the very evidence we seek to understand. It transforms our quest from a treasure hunt into a respectful dialogue with the past. As we reflect on this journey, from the impossible cuts at Puma Punku to the silent factories of Aswan, a single, unifying theme emerges. We are not just uncovering forgotten machines, we are recovering a lost chapter of human potential, a reminder that our history is far deeper and more inventive than we ever knew. The greatest lesson these stones teach is not about how they were built, but about the fragile nature of knowledge itself, and our shared duty to protect it for the generations of explorers yet to come. The evidence is no longer a collection of loose threads, but a woven tapestry of forgotten industry. From the parallel grooves of ancient saws to the spiraling cores of high-speed drills, from the lathe-turned perfection of stone vases to the earthquake-proof geometry of polygonal walls, the story is consistent. These stones were not shaped by brute force alone, but by sophisticated machines that applied relentless, precise power. This discovery shatters the conventional timeline of human progress, revealing peaks of technological achievement that were later lost to the quiet erosion of time. These silent monuments are a powerful tribute to human ingenuity, but they are also a permanent warning about the fragility of knowledge itself. Our own civilization, for all its digital abundance, is not immune to the same cycles of loss and recovery. This exploration invites us to look at the past with fresh eyes, to appreciate the profound innovations of our ancestors, and to commit to preserving our own advancements with the same care. We would love to hear your perspective on these enduring mysteries. Share your thoughts in the comments below, and if you are captivated by these deep dives into historical enigmas, subscribe to continue the journey with us. Thank you for exploring the precision of the past. Let us keep questioning, discovering, and ensuring that the brilliant chapters of human invention are never again allowed to fade into silence.